Welcome to the Graphing Polynomials lesson. Now this is a fairly long lesson, so I'm going to break it down into two videos, and it is a lot of information. Graphing polynomials is a very common question on the provincial exam. They usually like to have at least one, but usually two questions that are worth quite a few marks on graphing polynomials. So before we begin to graph polynomials, we're going to look at the characteristics of different type of polynomial graphs. So an even degree polynomial, that just means that your power, your highest power, is an even number. So that would be 2, 4, 6, and on. All even degree polynomials will have the same end behavior. That means that on your left side of your graph, the end behavior is going to be the same as the right side of your graph. And they'll both point towards either positive infinity or negative infinity. I'll point towards positive infinity when you have a positive leading coefficient. So that is when you have a number like 2x squared or y equals 4x to the power 4, something like that. Then both your arms are going to face up. In other words, your end behavior is going to be the same. Now, if you have a negative leading coefficient, then both your arms are going to face negative infinity. But again, both end behaviors are also the same, going towards negative infinity. Now let's look at the odd degree polynomials. You can see right away, that's a slight change here, that your arms are going in different directions. In other words, your end behavior are different. One's going towards negative infinity, the other one's going towards positive infinity. And it usually looks like an increasing function from lowest to highest when you have a positive leading coefficient. So again, we have a positive leading coefficient for this one. So we're going from negative infinity as your one end behavior on the left side to positive infinity for your end behavior on the right side. And if you have a negative leading coefficient, then it's the opposite. It's a decreasing function. So we're going to go from increasing to decreasing. So your end behavior on the left side is going towards positive infinity, and on the right side is going towards negative infinity. Okay, so this tells you how your end behavior is going to look like depending on even degree polynomial and your odd degree. And then here are the various different shapes. The main ones you're going to use is the linear, the quadratic, and the cubic. Quartic and quintic, you will be graphing these, but you don't really need to memorize the name or really know the shape of them specifically, because knowing the linear, quadratic, and cubic would be enough, and you can derive the quartic and the quintic afterwards. So your linear graph is one that you're probably really familiar with, the y equals x graph. It looks like it's just a straight line that cuts through. Your quadratic, you should be familiar with this as well, in the form of y equals x squared. And this is an even function, degree of 2. And your cubic, you should be kind of familiar with this one, y equals x cubed of that form. And then you're going to have different end behavior, and this time you have 2 humps instead of the 1 from a quadratic. So some terms we're going to look at that might be relevant is your local max point and your local min point. I wouldn't really worry about the saddle point for now. We're not going to really utilize that very much. But you should know that a saddle point is kind of like the same shape as your y equals x cubed graph. That would look something like this, where it kind of flattens out a bit as you cross a 0. So that is the saddle point. Your local max and your local min, these looks like smaller maximum minimums. They're not the complete maximum or the complete minimum, but they are kind of like the humps in your graph. Okay, so let's actually try to graph this. The first method we're going to look at is using a table of values to sketch a polynomial. This is by no means the best method on graphing polynomials, but it is a valuable method when you have no idea what to do otherwise and no idea what the graph is going to look like. So I'm just going to pick a bunch of x values that we can plug into our f of x to find their y values so we do have points to graph. So I'm just going to go from -2 and onwards up to 2. So I just picked these points. Should you always pick these points? No, because it really depends on the graph. Sometimes you do need to pick more variety of points so you can get the total shape of your polynomial. Because sometimes if you only pick those points, you're not going to get the entire shape of your polynomial. Okay, so I'm going to go ahead and plug in our -2 into our function of f of x. So every time I see an x, I'm just going to replace it with a value -2 so I can get the y value. Okay, so then we have -2 times -8 minus 8 plus 4. That's positive 16 minus 8 plus 4, which is 12. And then for our next one, I'm going to do the same process. But once I do it, I will get 2. If I plugged in 0, that's -2 times 0, which is 0, 4 times 0, which is 0, plus 4, so that value is 4. Then I'm going to plug in 1, and then simplify, and I should get 6. And lastly, if I plug in 2, I'm going to get -4. So I'm going to now plot these points on our graph. And I am also labeling the graph. It's very important that you do that. On the provincial exam, they usually like to see at least 2 points, but it's always better to provide them more. In this case, we probably need to provide more than just 2 points, just because it is a polynomial. Okay, so I'm going to go ahead and graph these. And I'm actually going to change the scale of this as well because our highest y value is 12. So I'm going to go up by 2's instead. Okay, so at -2 we have a value of 12. Then at -1 we have a value of 2. At 0 we have 4. At 1 we have 6. And then at 2 we have -4. So I'm going to connect our points in order from left to right. And that is our polynomial, and we're done. But you should always check to make sure that this is the final shape, because let's just say you don't know sometimes, depending on the graph, if this is going to actually come back up. And that's a very important piece of information that you do need to graph. But look at this, we have a cubic. So if we have a cubic, that means that we should have opposite end behavior, which we do, because on the left side, we're going towards positive infinity, and the right side, we're going towards negative infinity. And also, usually in a cubic graph, there are 2 humps. So if you think about our standard x cubed graph, it looks something like this. There are generally like 2 humps there. So we fulfilled that, and then we know we are done with this graph. So why don't you go ahead and do the next one on your own. This one we should have about 3 humps. So make sure you have that while you're graphing, and then do the same method, find out what the graph will look like using your table of values. Okay, so here's the solution to this one. I just need to change the shape a little bit. So if you use table of values, you do need to make sure you're going to have to do a little bit more here, because once I stopped at 2, I have 1, 2, and then that's it. But we know that we need 3 humps because this has a power of 4. So at the end here, I'm just going to curve it up so it looks like it's going back up. and then we know we have the right shape. We also need to have the same end behavior because this is an even degree polynomial. So I do need to have my arms both facing towards positive infinity. So if you use the same x values as before, it is not enough in this situation. But if you found another one for 3 and found its corresponding y value, that would have helped you in this case. But you could also just recognize that if you didn't find enough points, well, how many humps was I supposed to have? And what is my end behavior supposed to be? And then you can follow up from there. So I didn't find the coordinate for when x is equals to 3, and that's fine because I just need to know the overall shape. They're not super picky about stuff like that in the provincial exam, as long as you have 2 to 3 points, which I have provided, and that is enough. So we already have the general shape, and that's good. Okay, so let's move on to a different method. We are going to use the intercepts method, and this is a fairly lengthy method, but it is a good method, so we could graph for any sort of situation. I don't need to think about, well, what points do I need to figure out for a table of values? Like, am I going to be missing a point and stuff like that? Because this will show you the entire graph. So the first step we're going to do is factor first. And just take a note that this, whatever standalone number you see, this is going to be your y-intercept because we do want to graph that point eventually. Okay, so we're just going to factor first. I'll give you the hint that 1 is going to work out. Then I'm going to list all my coefficients in order. I can bring down the 2 and then start my synthetic division. So 2 times 1 is 2. Combining these is 1. 1 times 1 is 14. Sorry, is 1. And I have to combine it with negative 14. So that's negative 13. Negative 13 times 1 is negative 13. Combining 19 and negative 13 is 6. Then 6 times 1 is 6. Combining these is 0. So because we have a remainder of 0, we know that using synthetic division with 1 worked out. Now I'm going to write these as a product of factors. So we're going to start again. These are your coefficients, and your power is going to be 1 less than what you started with for the first one. All right. So now we have to factor again because we have x to the power of 3 in our polynomial. So I'm going to use synthetic division again. And this time, I'll just give you a hint that 2 can work out for this polynomial. So I'm going to bring down that 2, multiply that 2 with the 2 is 4. Combining 4 and 1 is 5. 5 times 2 is 10. Combining with the negative 13 is negative 3. And then negative 3 times 2 is negative 6. We're left with the remainder of 0. So again, I'm going to rewrite this as product factors. I'm just going to continue on with this so I can keep everything in place and not forget any of my factors. So this is x minus 2 coming from up here using synthetic division. This x minus 1 just came from before. Now we're left with 2x squared plus 5x minus 3. Lastly, we're going to factor this. 2x squared plus 5x minus 3. And I'm going to use the box method to do this. So our factors of 2 is 2 and 1. And factors of 3 is 1 and 3. I'm going to multiply across, so 2 times 3 is 6, 1 times 1 is 1, and I can achieve a positive 5 if I had a positive 6 and a minus 1. This minus 1 reflects here, so this is what belongs in my bracket. 2x minus 1, x plus 3. So we finally factored that. This means that I have zeros of x equals 1, 2, a half, and negative 3. Now I will draw a sign diagram. And I'm going to plot this in order on my sign diagram. So we have negative 3 as one of the zeros. Then we have a half, 1 and 2. Notice that I don't really care about the spacing between them because I just need to figure out what the sign is going to be in each interval. So I'm going to write some steps down. We're going to plug values of x within each interval to determine the sign for the interval. Okay, so what this means is that I'm going to plug a value between negative infinity to -3 over here to figure out if whatever number I get is positive or negative, because this will tell me what my arms are going to look like, if it's going to be above the x-axis or below the x-axis. So in between negative infinity to -3, I can pick any number that fits in between that interval. So let's just say we can pick -4. And I only care about if it's positive or negative. So I'm going to use the factored form here. So use factored form to do this. So let's just say if I plugged in -4. So if I had -4 from using our factored form, that's -4 minus 1. This is a negative number. Then the next one, -4 minus 2. That's again, a negative number. Then we have -4 times 2 is a negative, minus 1, it is still a negative. Then lastly, x plus 3, so -4 plus 3 is a negative number. So I don't need to figure out what the number is, I just need to know if it's going to be positive or negative within each of these factors. And we found out if you plugged in x equals -4 into each of these, they are negative. So overall, if I have a negative times a negative, times a negative times a negative, it's going to be positive. So from -infinity to 3 to -3, it's positive, which means that my arm needs to be above the x-axis. I'm going to repeat this process again for the following intervals. So I'm going to pick a number between -3 and a half. The easiest one is going to be 0. So let's just pick 0. 0 minus 1 is a negative. 0 minus 2 is a negative. 0 minus 1 is a negative. 0 plus 3 is a positive. So overall, this interval is going to be a negative, because negative times a negative times a negative times a positive is negative. Now we're going to look at, let's say, 3 over 4. So if we have 3 over 4, which fits in between a half and 1, this is going to be a negative. 3 over 4 minus 2 is a negative. 2 times 3 over 4 minus 1 is a positive. And then 3 over plus 3 is a positive. So overall, this interval is going to be a positive number. Then between 1 and 2, we have to use 1.5. Okay, so for our first one, 1.5 minus 1 is going to be a positive. 1.5 minus 2 is a negative. 1.5 times 2 minus 1 is a positive. And then 1.5 plus 3 is a positive. So overall, this interval is negative. Then lastly, between 2 and infinity, I can pick any number between there. We can just say pick 3, or you can pick 4, it really doesn't matter. So 3 minus 1 is positive. 3 minus 2 is positive, positive, positive. So overall, this interval is positive. So now let's analyze what this means. When you have a positive in the interval, that means that the arms must be above the x-axis. If it's negative in the interval, the arms are below the x-axis. Again, I'm going to write some steps on the side. The first thing you want to do is plot the zeros on the x-axis. Okay, so we have 1, 2, a half, and -3. I'm going to label our graph first and then plot them. Okay, so we have -3, we have a half, 1, and 2. Your second step is to plot the y-intercept. And our y-intercept, if you just look at the top here, we stated that it is going to be -6. So 1, 2, 3, 4, 5, 6. This is where -6 is. I'm going to plot that point. Now we're going to follow the rules of the sign diagram. Okay, so it says from -infinity to -3, so this portion of our graph, it's going to be above the x-axis because it's positive. So that means my arm has to be something like this, above the x-axis. Then between -3 to a half, it's below the x-axis. So from here to here, this section from here to here has to be below, which makes sense because we already have a y-intercept. So I'm just going to connect that point and then come back up so I can touch that 0. Okay, sorry, I'm trying to make this look like more a function, but it's just super squishy in here. Need this to look like a function. Okay, and then now from -2, so sorry, from a half to 1, it's positive, so I need to be above the x-axis. So from a half to 1 in this section here, it needs to be above the x-axis. So do a little loop above the x-axis so I can go back to a 0 of 1. Then from 1 to 2, I need to be below the x-axis. So again, just a little loop there because I need to connect my zeros. But our section is going to be below the x-axis. And then from 2 to infinity is positive. So then we can just have it go up, and we don't have any zeros, so we don't need to come back down. So that is our graph, and we are done. Yes, it was a lot of work to do that, but this is a very accurate graph. We don't have to worry about the shape. The shape's already given to us there. You just need to make sure that it looks more like a curve and don't connect them into pointy bits like that, okay? All right, so you can try the next one on your own. Please make sure you have a little X there because I accidentally made a typo. Try this yourself, follow the same steps that I've given you, and then I'll go through the solution with you. Okay, so your first step was to factor, and in this case, you don't need to use synthetic division for that. But if you did, you probably will get the same answer anyway. It's just a bit more work. Just factor out the x first, and then we did our normal factoring to get the other zeros. All right, so then your zeros are going to be 0, 2, and -3. In this case, your y-intercept is just going to be 0. So you don't really need to worry too much about that one because that's already included in one of your zeros. Then you're going to do your sign diagram. So you need to figure out what the sign is between -infinity to -3, from -3 to 0, from 0 to 2, and from 2 to infinity. And you just pick in random x values that fit within that interval to figure out if that interval is positive or negative. All right, so once you do have that, from -infinity to -3, it's negative, so you had to draw something below the x-axis. So you drew an arm below the x-axis in that interval. Between -3 and 0, it's above the x-axis because it's positive, so that's why you drew your arm above it. From 0 to 2, we got a negative, so that's below the x-axis, and then finally above the x-axis for the last interval from 2 to infinity. In terms of how high and low you go, it really doesn't matter, just because all we really care about is the shape. So all we really need to know is where are those zeros, what is the end behavior, and what is the shape. The only other point that you need to find besides those zeros is just the y-intercept, and in this case, your y-intercept was just 0. So that's all we're going to cover for this lesson. Please do the assigned homework because this is practice makes perfect.